Hi everyone, this is Russ Altman from The Future of Everything. This week we're running one of our best of episodes. In 2021, I spoke with Karen Liu, a professor of computer science here at Stanford. The conversation is relevant because, as we all know, AI is having quite a moment, and robotics, combined with AI, is going to be an important part of that. Karen and her lab are trying to get robots to help contribute to caregiving. That is to say, they're trying to help medical patients get dressed with robots. They're trying to help the elderly in their homes with robots. Their approach is to combine accurate physics simulations with AI. I hope you'll take the time to listen to this discussion. It's timely and relevant in the setting of a very large societal conversation about AI. Please enjoy. Before we jump into this podcast, let me ask you to please rate and review it. It helps us improve and it helps spread the word about the future of everything. We think of robots in Star Wars and our favorite TV shows from our childhood. Then we learned about robots in industry. They were assembling cars, trucks, airplanes. Those ones were disappointing because they didn't look like people. They looked like big cranes. And so I remember being, oh, is that a robot? But more recently, robots have started to enter our homes. There are toys, little fake pets that can run around, and little stylized humanoid robots. There are also robots used on the moon and Mars for roving and exploring. There are ones that can look into collapsed buildings during earthquakes, searching for survivors. And of course, in many ways, self-driving cars are a type of robot. My own first intense robot interaction or relationship is with the robotic vacuum that I have at home. And I must admit, I spent lots of time watching it navigate around my house, trying to figure out how it makes decisions about when to turn. And I often stand in front of it. We just have this whole relationship. Now, we all expect robotic technology will continue to blossom, and one of the big goals is to have robots that can safely interact with humans. Not just avoid them, not just not run into them, but actually interact with them on purpose. We have an aging population, for example, and we may not have enough human caregivers to do all the jobs that are required. So can robots potentially assist caregivers? What are the opportunities and challenges for useful robotic assistance? Well, Professor Karen Liu is a professor of computer science at Stanford University. She works on creating simulations of robots in order to test out different strategies for controlling their motions and all the decisions that they make. Karen, what are some of the current challenges in building the next generation of exciting robots?
Well, first, thanks for inviting me. It's great to have this opportunity to talk about robots and physics simulation. So there are a lot of challenges, but if we just sort of want to narrow down to this interaction between robots and humans, I think one of the greatest challenges is that we need the robot to be more intelligent. Not just about avoiding human, like you said, because a lot of time when you want to get the job done, you have to put a lot of the forces, like physical forces, on humans. And when you apply those physical force, large amount of physical forces on humans, bad things could happen. Right, and it really requires the robot to understand humans, the limitation of the humans, the boundary of the capabilities of the humans. And also it requires the robot to have some common sense. Like the human caregivers who usually have a lot of experience in common sense. So how do we build robots that can have this kind of a common sense and also have this awareness of a human is one of the biggest challenges I see.
So when you talk about your work, you often call it a physics-based simulation. So can you take us through why is the simulation important? What are the uses of the simulation? I guess you could just build a robot and see what happens. And then what does physics-based mean?
Sure. So physics-based simulation is a software. You can think about it, it's a program. And what it does is it's a way for you to predict what would happen in the future. And usually the reason it's a physics-based because it's a model that tried to emulate the laws of the physics. So just put a little bit, the technical terms would be we want to integrate a dynamic equations or differential equations, so that we know what the state what in the future the state of the world would be. So having a good physics simulation means that we could ask questions like, if I apply this much of a force at this particular moment in time, what would happen down the road in the future? And before robot make that decision, robot can sort of have a peak of what would happen, the consequence of its action.
And so maybe you could build in a rule that if you're going to hit the patient at a certain force or a certain velocity, that's too much, that's dangerous, don't do that. Something like that. Are there alternatives to physics-based simulation? So is there something else you could do but that you're not doing in terms of the simulations?
Right. So physics simulation is actually somewhat controversial. That's for the longest time, roboticists don't really trust simulation. They use physics simulation as a way, sort of proof of concept, prototype a particular components of the robot, but they wouldn't trust physics simulation to give you the final solution. And like, for example, Boston Dynamics, we have seen those really amazing results. They put it on YouTube, and many, for the longest time, they don't really use physics simulation to design their robot control policy.
So they actually did what I was talking before. They just build it and see what happens.
They just build it in the real world, and then test it. And if it breaks, they fix it and try it again with a different strategy. So you could do that if your robot. The purpose of a robot is to perform locomotion or manipulation without humans in the scene. That is okay. If you have enough of resources, you don't worry about breaking the robots all the time. This is fine. But about 8-9 years ago, people start talking about this concept of co-robots. We want the robot to leave the industrial setting. We don't put a robot in a cage anymore. We want a robot to actually have this really intimate physical interaction with the humans. And that's how people see, the future of robots. In that particular scenarios, physics simulation becomes really useful, right? Because you certainly don't want a half-trained robot or half-developed robot to start interacting with humans. And if you have a simulated environment with humans, with virtual humans in the scenes, then you can sort of test out whether the strategy of your robot is safe or effective.
Yeah, that really makes a lot of sense. So with humans in the loop, you don't have just what you just said. You don't have this luxury of just trying it out, because you really could do real harm to people. It's almost like a drug or a diagnostic. It's almost like an FDA thing where you have to make sure that it's safe before you ever get it anywhere close to humans. And so, and this is what your work focuses on.
Correct.
So tell me, I know that you've written a lot about this problem that you said about if we're going to interact with humans, then we have to be a lot smarter. And I could interpret smart in at least a couple of ways. One would be how the robot plans its interaction with the human, how it actually approaches the human. But I could also imagine at a much lower level, it has to be able to feel like soft things like skin or clothing. And I think you've worked on both of these. So let's pick one of them. Let's pick the feeling and the touching. What's the status there, and what kind of work are you doing to try to solve that part of the problem?
Yeah, so that's a very good point, because when you're trying to build a robot that can interact with humans, you have to think pretty much every component, from sensing, perception, to decision making, to actuation. So we definitely need a better decision maker, like usually we call that a policy, but we also need a robot that can sense people, that can perceive people better. And oftentimes when you are talking about applications like assistive robotics, for healthcare or rehabilitation, vision perception is definitely useful, but it's not going to be the only way to give a robot a good perception of humans. So, for example, one problem that we've been working a lot on is to teach a robot how to put clothes on humans. We call it, assisting.
Wow, that sounds like a really tough. That sounds tough. I mean, I just got I have a 2-year-old grandson, and getting his coat on is a remarkably complex interaction.
Exactly. Yeah. It would take 3 to 4 years for a human child to learn that. I mean, I have a 5-year-old boy. still he's not, perfecting that skill yet.
Okay, so I'm sorry I distracted you, but so
Right,
tell me about that task. Tell me about that task.
Sure. So that task it really requires the robot to have the modality of perception beyond just visual perception, because the purpose of addressing this is to use cloth to occlude the human body parts, and occlusion is always a big problem for visual sensors like cameras. So we had to develop invent new ways to perceive humans, and haptics, tactile sensing is one thing that we put a lot of thought on. So, can we tell, there's one particular project to make it concrete is that robot has those like force torque sensors at the wrist. And the robot doesn't have a lot of sensor, by the way, to start out with. They don't come with this kind of detailed tactile sensing like our human hand. So oftentimes the only thing you can do in terms of haptic sensing is to have, one of the most common things you could do is to have a force torque sensors at the wrist. So the question is,
just to make sure we understand, a force torque sensor is able to tell how much resistance the robotic arm or hand or whatever is getting, and how much twisting it's sensing and how much pushing it's sensing?
Correct.
Okay.
Yeah, so basically sensing any external forces or torque that you apply on the hands can be sensed around the wrist. But that's pretty low resolution sensing, right? You got 6 degrees of freedom, 6 degrees of the reading out of it. So from there, can we predict or can we estimate how much forces a robot is putting on human's arm or human's limb, human's body parts when the robot is trying to pull, let's say a hospital gown up a human's arm. And so basically it's a mapping that we need to learn. And that's when machine learning becomes very useful, right? Because we could actually learn such a mapping from data. And then that's
so
also
now you're going to be using AI, artificial intelligence.
Yeah, I usually call it machine learning, but yes. AI, I guess. So and this ties back to the physics simulation, because in order to train such a mapping, you need a lot of data and need a lot of labeled data. And physics simulation is very useful for many ways. And one of the prominent use of physical simulations to give you those ground truth label data. So we can actually use a cloth simulation to simulate the amount of force and pressure that apply on the virtual humans.
Yes.
And using a virtual robot's arm to pull that, and then you get this input and output mapping, and you can get unlimited number of data you want. You can also generate all different kind of variations, right? You can change the materials of the cloth. You can, So
then,
a lot of
now
data
you have a machine learning model that knows that has tried to put a thing on a human basically hundreds of thousands or millions of times, and the simulation is accurate enough that it can learn the principles of like what works when you're putting somebody's arm into a sleeve or something like that. Now, does it have to know about not only human arms, but also about cloth and the properties of a cloth?
Yes. We do need a fairly accurate cloth simulator. And then one nice thing about that is that A, you can get a lot of data, and B, you can get the data with huge diversity, right? So for example, I want my robots to know, because when you have a different material, elasticity of cloth, different type of garments.
Right, spandex versus wool.
Yeah, that's right. Yes, and in that scenario, if you want to learn all these from real world settings, to generate data, to acquire data from the real world, it would be very impractical.
And so this, I take it that you've done this and it works. In other words, the simulated gowning of the patient can generate enough examples that rather than having to watch a robot try this on a human hundreds or thousands of times, your simulations are good enough that you can then get performance. Has it gotten to the point where you actually then build the robot and see if it works, or are we still in the simulation phase?
We actually did that for a simple case of, exactly addressing putting a hospital gown on a person, because
Yes.
it's a simple case. It's designed to be easy to put on, right?
Right.
Hospital gown. So for that, we actually tested it on the real robots with the real people, and it works pretty well. And not because we have a good decision making. It's actually good. It's because we have a very good perception. That's haptic based.
Really? Okay, so that's very exciting. And so I wanted to also move in some of your writings and talks, you've talked about this gap between the simulation and reality. And it sounds like in this example, and my understanding of this simulation to get to reality gap, it's that you do these simulations and they're pretty good, but then when you bring the robot into a real system, it doesn't really work. So are we starting to understand the principles about how to make those simulations closer to reality? Tell me, just unpack that whole idea a little bit for me.
Sure. Yeah, so now we're talking about the other side of the physics simulation, which is when it doesn't work, right? So you can train as much as you want in simulation and it works great, but the ultimate test is still when you deploy in the real world. How does it perform? And that's what you mentioned, the simulation to reality gap, the sim to real gap. It's very, very active research area right now. There are a lot of strategies that people have tried, but in general, you can just think about there are pretty much just two things you can do. You can make the control strategy better in the sense that it's more robust. It doesn't matter, like a little bit of mismatch between reality and the simulation is not going to throw it off. So that's one strategy. Or you could just make your simulator better in the sense that it predicts the reality, the real world better. So we kind of sort of work from both ends. And when you're talking about scenario with a human in the scene, a better policy or better strategy could mean what we just talked about. It has to be human aware, right? You have to really understand the human states, human behavior, and being able to predict what humans will do in the future. If you have that capability, then you can have a better policy. In terms of a better simulators, since human now is part of the environment, the world that we're trying to simulate, so we need to model human better. And that is actually a really interesting research problem because there's so many ways that you can start, right? Like you want to make the human perception better, or humans behavior level, or the actuation level, where you kind of get into biomechanics.
So are you saying that you have to actually start simulating how a human might respond to the forces and the experience of having the robot put the gown on? And this is like what I was thinking about for my grandson, because he does random things in response to my attempts.
That's actually easy to model.
Oh, it is?
If it's a truly random, that's great.
Oh, good. I will tell him that. But then that sounds to me like it would be very challenging, because there you have to have some kind of model of the intentions and the goals of a human person being helped by a robot.
Yeah, that's exactly right. When we're talking about this highly unstructured, highly interactive scenario between human and robots, modeling human behavior becomes really, really difficult. I mean, we know pretty well how to model human gait, right? Even manipulation, we know how to do that because it's highly constrained. But when you in the scenario, you're trying to put a sweater on a 2-year-old boy, and how to model the response of that boy is hopeless. So we need to start somewhere. And one place that we've been looking into a lot is to not first let's not jump into this behavior level or cognitive level too quickly. Let's just see if we can have a really good physical model of a human, meaning that we can have a very accurate boundary of humans' kinematic capabilities and dynamic capabilities.
So how they move, where they move, and what their shape is.
Right. And then we want to make sure that you don't the robot is not going to force the human to act beyond its capability. So let's just start with that, like a feasibility problem, right? We want to make sure that whatever we do is safe, and we can first start with the assumption that human is cooperative. right? The goal of a human is to get that close on. So it will try everything within its capability to make this happen. And that is a very, very strong assumption, but it's also an assumption that allows us to progress in this sort of very daunting problem domain.
We were talking about this amazing and I think challenging task of having a robot help a human get dressed. And it occurs to me that there are a lot of issues about what the robot looks like, whether the human accepts the help. Is it a scary device? What is the relationship? Has that even been looked at or thought about yet, or is that too far into the future?
Well, that's a really important, research problem, and it has been looked at not by us, not by our lab, but just a few examples we have is when we actually tried this assistive dressing robot on our participants. One common complaint is that people don't like the robot's arm end effectors being so close to their face, and that sort of things that we haven't thought too much about. Although we have not directly addressed this the issue of trust, one thing that we are looking into is that we're trying to figure out a way to transition humans, or sort of like give a human a tutorial how you actually interact with robots before it actually happens. And physics simulation is again one really useful tools that you can actually see how the robot and human interact in this animation, in this simulation first, and then next step will be we'll put human in virtual reality with a virtual robot and see how they interact with each other. In that case, you can actually use your body movements to have this physical interaction with the robot.
So then if your virtual
happens.
reality robot is putting its arm in your face, they might move back, and then you could say, we forgot about that. We have to make sure there's nothing. Okay, so there is going to be like this human-computer interaction science to figure out how to develop a trusting relationship and know that this robot is not scary, is not going to kill me, and is just here to help.
Yes, definitely. And then also there is the one element which is very hairy that we have not started looking into. That's the adaptation. Like once you have the real humans interacting with the real robots for a period of time, human would change. And how do we actually adapt robots to accommodate the change?
Because if you make the assumption that the human always responds in the same way, that would be a disaster, because the humans will learn what the robot is good at and what it's not good at, and they'll try to help it. And if the robot doesn't realize that this is an evolving partner, it could do the wrong thing.
Yes, that's definitely right.
Well, I wanted to move to a different topic, which is related but quite different. It's almost like where the robot and the human become one, and it's this research projects that you have in the area of exoskeletons. So I guess the best thing to start with is if you could define for me what is an exoskeleton, and what is the approach that your group is taking to this problem or this challenge?
Sure. And this is a relatively new research area that we just start investigating. To define exoskeleton, I think one way to think about is a wearable device. You think about robot as something that you can wear. Like you'll become part of that whole entity. And
we've seen like Iron Man and the movies, right? It's the same idea that where the human is inside and is getting augmented by a robot that surrounds it, basically.
Yes. Yeah. So the human should be able to do whatever human would usually do. The robot shouldn't, the exoskeleton or wearable device shouldn't impede humans' like range of emotion, for example. And this particular problem we're looking at is an exoskeleton that assists humans walking, specifically preventing humans from falling. And because with the exoskeleton, if a human is willing to wear that already, then we should take advantage of that, right? We can put the sensors in as much as sensors we need, and so we can predict if a human is about to fall. And if that happens, then we could have the exoskeleton itself to actuate to basically
correct the posture or whatever.
Yeah. And that's sort of the first step we're looking at. And we're also thinking about putting cameras on the exoskeleton as well. So you can imagine there's outward-facing cameras. So in many ways, the exoskeleton understands your environment as a context, right? So you can measure your sort of inertial property, your center of mass, and all those things. But at the same time, it also understands which environment you're in, right? So if you're right next to a chair, then this robot can have some kind of assumption, can make assumption about what's going to happen in the future.
So that sounds like some of the self-driving car technologies might be transferable, because they're also in charge of not running over chairs and stuff like that.
Right, definitely. And yeah, I think that's a very, very good analogy. You can think about a robot is your robot is driving you around. Robot knows the environment and it can steer your direction.
Now, are you, because you're an expert at these simulations, are you initially approaching this exoskeleton problem from the perspective of another physics-based simulation?
That's correct. We started out thinking how we can model the human behavior in simulation. When we train this exoskeleton, you can't just train it with a passive or static human
like
model,
a floppy
right?
doll, because a human is not a floppy doll.
Right, rag doll, right, like that. We will have to assume human has the capability of locomotion, of walking, but so that becomes really interesting to think about what's the capability, the range of the capability of the humans, and when should we interfere. Another thing we really want this exoskeleton to have is that it should only be activated when it's needed, right? We don't want human to depend on that too much either.
So that's very tricky, because then the exoskeleton has to make decisions based on what it's seeing the human doing. Do I need to intervene, or can the human handle what they're doing without my help?
Exactly. So that's
once again, you need a model of the user, so to speak.
Exactly, and predicting its intention, the virtual or the human's intention, is really crucial.
Are the main applications of this, just as we finish up, the main applications of this, I would guess, are in rehabilitation medicine and for people who've maybe suffered strokes or have walking deficits? Is that the initial application area where this is likely to be unrolled?
Yes, yeah. So we probably will start our pilot study. Probably will be focused on older adults. So people still have mobility. They can still move around in the indoor scenario, but it would. But they're they can definitely benefit from this kind of system.
This is very important work. Even as we speak, my father is in the hospital because he fell last night and he couldn't get up, and he'll be okay. And I've gotten good reports. But this is exactly the technology that he and many other elderly will need. You have been listening to the Future of Everything podcast with Russ Altman. I want to remind you that the Future of Everything started out as a radio show on SiriusXM, so you'll hear references to that. Now it is 100% podcast, but we still have access to the great shows that we taped with SiriusXM. There are more than 215 of them, and they cover an extraordinary range of topics. If you're enjoying the podcast, please consider subscribing or following so that you can be alerted to every new episode and never be surprised by the future. Maybe tell your friends about it too. Definitely consider rating and reviewing it. That helps us grow, improve, and also spreads the word. You can connect with me on Twitter @RBAltman and with Stanford Engineering @StanfordENG.